So my name is Joe Sherwin. I'm Principal Solution Architect in the North America for Hazelcast. So primarily because of my geographical location, I deal with a lot of financial customers. I've been with the company since 2017, by the way. The other thing I want to get out of the way is that we're giving out a prize at the end of this. So if you have your phone out, again, you can snap the QR code and register yourself for that. Hopefully that'll work resiliently. So go ahead and do that. Not sure what's good for $100 on Amazon right now. Scarf. Yeah. Snowshoes. Yeah, I don't know. I'd probably go for a little more than 100. Yeah. All right. Let me know if you want to do it, or if you walk in late, anyone walks in late want to do it. I'll go back to the slide. So the agenda for today is really talking about the core patterns for designing fault-tolerant system, monitoring these distributed system, and failure-aware design. And then we'll have a little demo of that, of those concepts, working in a chaos kind of simulated chaos type of a situation. So yeah, like I mentioned, there's lots of pieces of the puzzle when you're talking about designing for failure, JVMs, memory issues, garbage collection, VMs, vMotion. I don't know if everyone ever had a problem with their application being vMotion on a vSphere system. That can cause issues. Host issues. You lose a node, lose a VM, lose a pod. Network, power supply issues. All those things are can cause your components to crash. And how does your system heal or react to that, or is it still available or not? Is one of the architectural concerns typically of some of these applications that I deal with at the banks, that where they're high value, always on, payment systems, for example, being able to assure 5 nines availability when events like this occur. It's a challenge. So obviously, I think a lot of people are familiar with the single point of failure issues. One of the other most common neglected concern for single point of failure has to do with your system of record. Your system of record, typically, if you've done everything right at your application layer, might be your single point of failure. We kind of learned, a lot of companies learn to accept that, but we'll see that you don't have to. And defaulting to safe state on errors, fail fast, those kinds of things. Switching to read only rather than going ahead and allowing mutation operation. So if your system can say, you know what, I may not be able to guarantee that it can mutate things for you, but you can still have read access to the data that I do have. So that's a possibility when you're thinking of contingencies for failure, managing failure. The other thing we want to stress is we, as developers, when you're sitting there, you've read the design and you're implementing a solution, you normally don't really think about that, and usually there's someone who's supposed to be thinking about that for you. And providing, if you're writing a component or you're implementing a component, you're making sure that you're able to publish statistics, get statistics from that component, especially if it's a critical component. You want to give the higher level monitoring systems the ability to proactively make any kind of actions that they need to in order to prevent something that might be failing. So being able to publish and monitor, at least publish your statistics so that any kind of active monitoring can take advantage of thresholds that might need attention and create alerts so that the ops teams can respond to it, either dynamically or manually. Does anyone design systems with metrics in mind? Yeah? One? Yeah? Yeah. We kind of, like, as developers, we kind of assume that, for example, if you're a Java developer, right, you know you have JMX, and you can monitor the process itself and maybe some of the statistics on the machine it's running, but you never think about, the logical component you're writing and what its metrics and what its, is it measuring how many requests it's getting per second and things like that. So you're hoping higher level there's something you can read that can tell you that, but if the metrics cannot tell you what it thinks its health is, or if it's not designed to predict that it might be in a situation, if it could be designed that way, it would be much more helpful than being too late when you start seeing the system side effects of a situation. So one of the two concepts in fault tolerance systems has to do with consensus and leader election, especially in a distributed system, which is what we're talking about, is distributed systems, right? So distributed systems is components that are clustered together and can behave and work together in order to provide functionality to your solution, right? So leader election is a process of choosing a single member in a clustered solution as the coordinator. That way, each member takes its instructions from that leader. That leader does other administrative things as well, coordinates other administrative things behind the scenes in order to maintain certain guarantees about maybe consistency of data, state that you're saving. Typically, that's the key one. But it's really about breaking the symmetry amongst known and picking one leader, ensuring that the one entity is in charge of avoiding any type of conflicts, right? And the popular ones you probably hear about lately is Raft, which is the consensus algorithm, and Kafka, which uses that particular one, well known. Any other leader election or consensus algorithm anyone want to have experience with? Okay. So we'll talk about some other ones, right? So besides RAF, obviously Paxos and Ring are two others that are well known, and they're well known for particular reasons, because a lot of time they deal with majority consensus and assure consistency, CRDT data types and things like that, coordination and fault tolerance behavior. If the leader fails, for example, in the algorithm you're using, what happens to the system? Okay. If the system gets into a network split, if you're dealing with a majority consensus, obviously you'll know that if you keep your odd number rule, you'll be able to figure out which cluster has a consensus, or which cluster partition has a consensus. Are everyone familiar with these particular algorithms? So the reason why I ask is that we don't really usually, as developers, think about such complex topics, right? We're just hoping whatever platform we're using, the framework we're using, has infused our application with these capabilities, and there are secondary concerns, right? And what I'm really saying here is that not true, especially into what we call today modern applications, microservices. Microservices are really built for stateless behavior, and it's a challenge for stateful type of transactions in microservices, so there has to be some coordination. And the coordination in microservices is typically, you have to call some other microservice, you have to do some compensating transactions or other things like that. You really don't understand, you don't really have any grasp of the state and the communications around multiple components or the same microservice, multiple instances of the same microservice. And how do we infuse that fault tolerance and consistency of state in a microservice? And when we're looking at a particular platform or framework that we're using to build these apps, we have to understand, what is the comparative strengths of the different types of consensus algorithms that platform may actually implement. So, in Hazelcast we use the RAF algorithm because it's quite easy and quite simple and straightforward. But it's also one of the more of the strongest implementation for consensus algorithm. And it's used in, as you can see in Kafka, used in a lot of the modern distributed systems. And in Hazelcast, like Spring or any of the Spring frameworks, it's simply part of your application. It's auto wired when you include Hazelcast in your dependency, and gives you this ability to share state and do what we call partitioning of data. So state data information that you're storing, whether it's microservice saying, hey, I'm working on X, and it's putting that state into memory in cache, and then any other microservice attached to the cache can check to see what the state of that X is, and determine whether or not to move on to something else or wait for that change, that state to change, right? So now you have this ability to do inter-process communication in a consistent, fault-tolerant manner, okay? And we'll see why it's fault-tolerant in a minute, and that's part of the demo, by the way. So partitioning, again, you might be familiar with the term sharding. So there are two types typically of approaches people do to store state. They may do what we call mirroring, where the copy of the state is in each member and it's written to each member. So that means you have to do, in this case, 3 writes, which may be across the network. And then there is partitioning, where you actually store a subset of the data on each node, and also you have a backup as well. So in case of failure, there's a backup that the leader of your cluster will be able to promote to primary on one of the remaining nodes, and then create a new backup copy, which will give you that fault tolerance automatically without your code ever having to be concerned about that situation. So again, the purpose of partitioning basically is scalability, load distribution, the ability to spread across nodes. Nodes can mean physical machines. Being able to query those partitions as well. So when you do submit, or if you're doing a key value store, and you ask for key XYZ, you know exactly which member in your cluster to go for that key, rather than having to send that query across each member. That is some of the underlying performance secrets of certain products. Some products they say, okay, we're going to send we're going to cast the request, the operation request, and the node that has that key will respond. In a replicated storage situation, reads a lot faster, and any member can respond to a request because there's a copy of the state on each of the member. But again, what you lose there is the ability to increase your write performance and to scale up. So when I add a new node to a replicated system, if this was replicated and I add a new node, I have to do a full copy of my data on that new node. So now each node has to have the same amount of memory, a large amount of memory, so that the entire content of my state needs to be able to be stored on each node. So a couple of strategies: redundancy, fault isolation, containing the damage to a component. So if I know a particular node is out of the cluster, I know what the subset of data might be that's been missing, and I can recover that. Automated failover. So if I got to maintain the availability during failure. So the members, the lead member typically, again, that's when you do leader election, that lead member can coordinate these activity. If the lead member was the one that was lost, how do we elect a new member, or can a new member be automatically selected and seamlessly selected to manage the recovery of any missing data set in the lost member? The other part of this is self-healing. So if I lose a partition of my application and it comes back on the network, how do I resolve that? Okay. Hey, I have data here. Now you also have the same data. What do we do here? Is it the ones that was last updated? Was it the ones who were in the majority? Those kinds of algorithms for doing self-healing, and whether or not you have any kind of say into how that actual self-healing is managed. Last updated, things like that. Being able to set those self-healing algorithms, configure those for your use case. The key point is distributed applications. They can be resilient, but obviously not indestructible, right? So it all depends on how many members of my cluster that I'm going to lose. Is my cluster even split into? If it does have a split brain situation, is it split into any of those splits actually have a majority? If I'm doing a majority consensus algorithm, and if I'm doing backup copies, how many nodes can I lose concurrently without losing a copy of the backup? Okay. So right now we're going to take a look at a demo of this. Any questions so far? Anybody have experience with this? Any real-world experience that they've seen issues with their systems they want to talk about and bring to the group?
Yeah, I introduced Hazelcast in one of the banks.
Which bank? You say which banks? TD, okay, our favorite.
But broker specifically, backend was not using Hazelcast up until a point, and then we had a lot of memory savings and speed improvements. Where are they right now? I'm not sure.
Yeah.
But I've heard that Hazelcast Hazelcast has been adopted across wider teams as well since.
Yeah. Bill can attest to that. Bill, I think, is the account executive for TD, actually.
Within TD, we actually just met with them today. They're actually starting to do some interesting projects around more of like on the event processing side, streaming and so forth. So, really interesting stuff that they're doing.
Yeah, I'll have some follow-up questions that might be a little bit harder to answer, but I'm very curious to talk about it.
Yeah.
For sure.
Yeah, so I'm gonna start this demo. So this is a multi-layer application example. So we'll deploy the what we call the middle tier of the application, and which basically is a clustered state storage, which is Hazelcast in this case, and we have something in Hazelcast called Management Center. So we publish all the metrics. So each node of Hazelcast uses JMX or REST in order to publish the statistics. If you're running in K8, you can publish through Prometheus Exporter. You can grab a template and put that in Grafana and grab the metrics and alert from there as well. But we'll see that happen here. So at this point, the most important thing for me is like, well, I don't know what the state of my system is. So I need to be able to monitor that system. And in this case here, let's reload that guy. It's pretty easy when it's stateless. So let's go to the cluster. So let's go here. Let's start from the beginning here and look at so with this tool, this management center, hopefully let me make it bigger. There we go. Obviously I can monitor more than one cluster at the same time, but typically what we want to do is one-to-one with the cluster it's monitoring. So there's fault tolerance, again, no single point of failure, even in the management tools, right? That's a key point. If I can't connect and see what's going on, all the alerting that I've done is moot. So having no single point of failure, even in your management tools, is a key understanding that you need to have a resilient system. So here I can see the metrics. I can see each member in my cluster. I can see I have 5 members. I should have 5 members. Yeah, and I can see CPU. Obviously, these are kind of things that you normally get from a Java process that's running. But also, I can see if there's any state information. I can also see if there's any operations that are going slow. So remember I said that you write a component and you know the operations you're doing. It might be a business operation, okay? Debit, credit, something. And that you want to give a name and you'd want to give it some statistics because it may be different than the other operations that your solution is doing. So when you put some sort of metrics framework around your request, then you can actually alert on them, okay? So Hazelcast obviously knows the operations, knows a way of tracking the operations that a client might do. And the simplest ones is either put information or get information from Hazelcast. There are others, there are queries, there are compute requests that can send to the system. So the data's memory, I want to compute the average of the accounts. I can send that. I don't have to actually pull that into my microservice to do that and shuffle data around. I can simply send an algorithm to Hazelcast in order to do that computation for me, and it will actually go to each of the nodes and find the relevant accounts and do that calculations and do a scatter-gather type of behavior. But the key here is that these operations are being monitored, and I have a threshold that says if the operation is below X number of milliseconds, then you throw an alert on my slow operation system. And so now my Grafana, I can set a alert on this, and whether it's a email or manual operations I have to do, alert someone, I can do that. So I have that insight, I have that metric. Before the system gets to a point where one of the nodes are gone and we've lost SLA, I can be proactive on that. So storage, state, the most frequently used storage item is what's called a key value map in Hazelcast. Now I have one called customer here. And like I said, you can query these things. Let's see, this customer. So I'm able to create a query. In order to do that, basically I want to be able to do SQL type queries. I'm going to map my object map in order to Hazelcast will create what's called a virtual table with its query engine. So it's basically converting the key value map into a RDBMS-like table, and it's able to send queries to it. So once I do that, I should be able to now execute a query and look at the attributes of the objects. Okay, so it'll give me the ability to inspect things. It also a client can actually use the query API rather than use a key value API. So you can have any type of client with Hazelcast, Python, C++, Go, Node.js, .NET, as well as Java, of course, and submit queries. Even if the system cannot, if you're doing is not able to deal with the object type or how the object is serialized, you can actually query it with that language. So one of the things we want to do when we look at the data, I'm going to populate 2 maps. Let me see if I can get this guy down. In order to do this chaos testing, okay. So I've added 10,000 generated entries to a map called critical map. That map has a backup count of 4, and I put the same 1,000 entries in a map called cache map, and the backup count is set to 0. Right? Let's go back to our management center and see what that means to us from our data state storage standpoint. When we look at our maps here, you can see the primary entries for each map, 10,000, and the memory as well is the same. But when you click, let's say click on the 4, you see that the data is distributed across each member in the cluster. But what happens, this is the cache map, and you can see there is no backup for this cache map. Or the backups, or there should be at least 4 backups for each of these. Am I the right map? Let me. Oh, wrong map. Sorry. I was like, what is he doing? Wrong one. Cache map should have no backups. 10,000. You can see the number of puts that I put in there, and of course 0 backups. Okay, and the backup memory usage is 0. When we go to the critical map, 10,000 puts, but 40,000 backups, right? So 4 backups per entry. Okay, what does that mean? I can safely lose up to 4 nodes, 4 or less nodes without losing any data. So when we do something where we simulate some kind of a chaos where we get, let's see, we try to kill -9 subset of nodes. Oh, actually, before we do that, what I wanted to show is if I can do so what happens if I add 1 node? Now, it's happened already. Let me just reload this. This guy is, yeah. Oh, that's probably what it is. But I can, I had the wrong node count. Let's do that again. Let's see what we do here. Okay. So I'm going to take, the leader is usually in Ref, the first member that joins the cluster. So I'm going to take a majority of these members, and I'm simply going to kill -9 them. Just like that. And then we go back to our metrics.
So you killed 3 out of 5?
Correct, yeah. So we're left with 2. And now we're going to see, well, what did that do to our state? It's hard kills. So yes, oh, look at that. There's still 10,000 in critical map. And we've lost some data in the cache map, which has a backup count of 0. So as expected. So being able to configure that behavior is huge. Normally, a lot of systems don't give you that option. You can say, and the default option, that's what you're going to see, is the other maps that I created. They're using the default option of 1 backup, and they've lost data as well. Okay? So in certain use cases, especially in bank use cases, there's some sensitivity to loss. The fault tolerance nature and the consistency nature of the solution can depend on the business use case. And being able to configure that and say, hey, and tell the business, hey, you can lose up to 4 nodes in this cluster, and you should not lose any data. Okay? And how does that happen? So a lot of the times, these are self-inflicted situations where you have this failure. Your infrastructure team does a repave. They do an update on an OS, or they do an update on Kubernetes, and you start losing pods on instances. What does that do to your data? What does that do to your SLA? You may say, you know what, I can live with a degraded SLA, but I cannot have incorrect information or inconsistent information. And that's where resiliency depends on the use case, and the amount of the resiliency you get may be sufficient for what you're doing, or insufficient for what you're doing.
Can I ask
yes.
Depending on how much time do you want to spend to that? Because this is a very interesting and very important example. But this is like classical, right? Like very book example.
Yes. It's very engineering, yeah.
What if you imagine you had a bigger cluster of, let's say, 10 nodes, and you had the same collection, 10,000 entries, with a backup factor, replication factor of 4, and then you killed half of the nodes in your cluster? And it's not about RAP, not about leader, but it impacted some replicas of the data, and now to achieve the replication factor of 4, you need to redistribute your backups among the surviving nodes.
Yeah.
Until that happens, the cluster is in a very interesting state. Like it can operate but it also probably needs to do some locks. So
Right.
you can redistribute the data to achieve the same replication factor as per control.
So that's literally where we're going. So we see that we're not at 40 anymore. So there is alerts happening in the logs right now saying that we're not at the specified threshold for backups. There's another concept to what you're talking about, is if I lost, let's say I have two actual physical instances in Kubernetes that I've as part of my Kubernetes cluster. If half my nodes were on this one and the other half was on this one, and the backups were also co-located in the same instance.
You're talking about affinity?
The affinity, yes. So being able to tell your backup algorithm that, you know what, I don't need the backup for the primaries on the same zone or the same rack as the primary. It has to be on a disparate rack. So that's another level of fault tolerance that it's able to be configured as well. So you can literally say you have to be in disparate racks in order to store the backup for me. Yeah. So those are things like that. So when they decide to do a node Kubernetes instance repave, you have to know your Hazelcast is probably spread across multiple instances, and you have to set that node affinity or partition behavior so that the backups are in disparate instances. And the clustering capability has this concept of, I know the environment where I'm doing discovery of the other members. So I'm using Kubernetes discovery, and I know that I can get information about which instance that the pod is on. So it knows not to place any primaries on this pod, on this instance. Their backup should be on a disparate instance. So those are the higher level capabilities that's specific to Hazelcast and unique to Hazelcast, actually.
You're going to talk about how the backups are going to be redistributed amongst the surviving members?
Yeah. Yeah. So what happens is, so this is where the leader comes in. The leader decides and says, okay, which partitions, basically that backup and recovery, we call it promotion. He's coordinated in a transaction using a transaction mechanism with the remaining nodes and the remaining backups in order to recover the data. So any missing partitions, if you say, okay, I've lost too many and there are missing partitions, that will be alerted in there as well. So you'll literally know that you're missing partitions, most likely because you're in a segment of the cluster that does not have a quorum. The other thing that could happen is that, I don't even have enough memory, right, to store all the backups as well. So then you might see memory usage pressures and memory alerting and things like that while it's trying to do that redistribution as well. But the key to that also is, while that redistribution is going on, can the service be called? Can the service, can I submit operation to the service? And the question is, yes, because we are doing batches of partitions in the promotion and the new backup. We're not doing all at once. We're not tying up all the partitions. So any partitions that's available to be read, that operation will go through. Any partitions that are being repartitioned, your operation will wait for that. And tuning how fast that's done, that has to do with your data size as well, and the number of partitions that you specify in the system.
Tiny follow-up. Reads and writes are locked up?
By default, reads and writes happen on the partition thread that's controlling the partition, yes. So that's why we give consistency as well. Yeah. You can say read from backup if you want to optimize reading and you don't care about the latest data or things like that, yeah. So it's a little geeky and a little under the covers, but the beauty of this is that as a developer, when I use Hazelcast, this happens. This is happening by default, and I don't ever really think about it. So I'm getting it for free, and I'm getting it with a peace of mind, because there's not much that I have to know about. Besides this discovery and making it zone aware, that's one of the configurations that happens in the file. But when we look at let's look at that. Hopefully. So basically, what I've created, this cache map and the critical map. I could have done this with Java APIs, but here do it with YAML or XML. And here I'm setting the backup count. The other thing about Hazelcast is that backup count is synchronous configuration. We also have an async backup as well you can do. So some of my customers said, you know what, we don't want to take the hit of the performance of synchronously. Every time we make a mutation to an entry, we have to write 4 backups, right, or 3 backups.
Transactional versus non-transactional.
Yes, yeah. So yeah, asynchronous versus synchronous on the backup. So people say, well, other products, all their backup information is asynchronous. So as I'm changing this guy, my backup, the changes that I have to apply to backup lines up in a queue that may or may not be fault tolerant, and the state of my backup is behind. And if my system failed during that time, I will have stale information on that backup. So if your backup is not synchronous, then and you do have a replicated backup system like vanilla Redis does that. You go to the backup, your data might be stale because the leader is the one, the master is the one that's actually handling the writes of the backup asynchronously. He fails, you're done, because you may have stale, especially in a high transaction system, high updates, you'll have that issue. Okay. There's another concept that goes further, and we're going to explore that right now. And that has to do with, well, this works fine. I'm in a single region. I'm in a single data center. That's great. I have local fault tolerance. But what happens if the entire data center goes down, right? So we'll talk about that now. I'm going to restart the demo at this point. Okay. We'll do a check, health, and we'll do a startup. And what we didn't talk about behind the scenes, what's happening is that that cluster that I was running before, he's configured to replicate his state to another cluster, and we call that WAN replication, geo-replication, another term we use for it, and that allows you to be able to not just in a real disaster, like you've seen the Amazon outages of regions. What happens to my application in that situation? Can the state of one region be replicated to another and have a limited impact on my service availability? Or no impact at all, depending on what happens and when it happens. So let's let's do it in another screen here. And let's put that a little bigger. So I'm going to start my microservices layer. Okay. We're going to see what this application actually does in a minute. Let me just make that bigger too. We're going to start the web front end and the microservices layer of the application. The application is called Borg. You can see it loads up the state here. And Borg is an acronym for Big Online Retail Giant. You definitely do. I'm glad someone got it finally. But so, and then I'm going to simulate transactions coming to this retail giant, and you can see it connects to cluster A, and we can see that. And we can, so we want to, again, metrics important. Let me refresh this guy here. Let's go to cluster. So one of the things you'll see is that I have actually a Borg A and a Borg B cluster, right? There are things happening in Borg A right now, it's up. Borg B is not up. I'm going to turn on that cluster. What you see here is there's a WAN replication queue here, and it's filling up with information that it wants to share with the other cluster. It's also doing some sort of acquiescing of the data so that it's only the latest information per key and not every single write, so it doesn't take up your memory. And if I do a start, oh, come on now. So cluster B will come up, and we'll lose those warning issue on the replication. I'm impatient. Let's see. Come on. Start seeing a couple of these guys start replicating. The management center right now is polling, so it might have been completed a long time ago, but each page has a different number of seconds that it polls on, so I force it.
What kind of replication is that? Is that kind of a active-passive or active-active?
Active-active, two-way replication, and we're going to demonstrate that in a minute. Yeah. So what you can see. So in order to demonstrate that, so now I have both clusters up. I can go over here and look at them. Both have 5 members. Borg B. The data should be in sync at this point. Good. And you can see, we should see 5 maps here, 5 out of 9. It says 5 out of 9 because there are some hidden system maps in there as well. So I should have 1,000, 10,000, and this particular transaction map should be growing actively. And one of the things we want to show you that this is a two-way replication. So we have a script, and this script is going to arbitrarily put data in a map. The map is not predefined. It's going to dynamically create the map. So in this case, I'm using the command line client, and I'm going to arbitrarily create this map called default map, and I'm going to put 3,000 entries in there. But it's going to connect to cluster B, and we're expecting to see the map is not in. The map should be created as well in cluster A. Okay. And how do we tell whether it's the operation occurred in cluster B and not A? And that's the other interesting point here. So when we go to our metrics, and we go to, so we're in cluster B at this point. We see we got a 6 map now, default map. And what we'll see on this default map is the number of puts that occurred on one of the nodes, because the CLI goes to just picks a single node, but the data is distributed across all the nodes based on the key. Now we go to cluster A, and there should be 7 because I hit that other guy, but default map. And what we're looking for is there's no puts, but he has the same amount of data. Okay? So we know that the actual mutation operations, put operation occurred on that cluster, and this data set was replicated. Okay? So the question is, what happens now? So I have this service running, give me a dashboard in my web app. It's using my service layer to create that. Okay, that should be growing. Let me just reload just to make sure everything is snappy on this guy.
Quick question.
Go ahead, please. Yeah, I'm getting alerts.
What type of consistency guarantees are available with geo-replication?
Yeah. So with the replication, the WAN replication, it's eventual consistency. With the localized, yeah. So.
But with like this geographically distantiated, there's no options for strong consistency.
There's options. There's no option for strong consistency when you're doing the WAN replication. What there is options for, if you distribute what we call a CP distributed object to store your CP map to store your objects, you can actually have strong consistency across across geographically distributed cluster. Obviously, there's a performance price for that. Yeah. So basically, what it means, you'd have to create a cluster that spans geographical areas. Yeah, so latency issues. So there are some specific use cases for that. And it has to do with payments and keeping payments counts and things like that. That customers require that for that use case. And typically, they try to keep it across not geographical, but maybe East 1, East 2, or East and West U.S. type of. But when you start going to Australia, that's you're going to pay a price for that, yeah.
But that was at a certain point a $1 million question in the banks, right? Because their legacy architectural requirements need geographical distribution.
Yeah.
At a certain distance.
Yeah.
And many technologies don't want to have clusters stretched that
No.
far.
Yeah. I mean, even on the file level. If you have synchronous file replication, if that breaks, you have to restart the whole process again. So it's really difficult to do it across huge geographical distances, speed of light situation, and it's ridiculously expensive. It could be. So and on the application layer, strong enough consistency, but performance sometimes trumps all of that. So if I can increase the throughput of my payment system, I'm decreasing my margins on the fees that I'm collecting, and I'm not missing any SLA and not paying out any penalties. So localizing the payments by where they're coming from and having individual clusters to process them. Yeah.
Just saying that, by the way, these conceptual difficulties are all shared across distributed systems, whether we are talking databases, Kafka, caching like Hazelcast, Greenplum, or...
Yeah. Well, what I was about to show you is that I can tune the WAN replication, even though it's eventual consistent so well that I may not even miss that number of transactions as it's going at that particular rate. So if I kill cluster A right now, which is where this data is coming from, the microservices will automatically fail over to cluster B because they're configured to see both clustered. And they're using the first one as a primary and the second one as a backup. So there's a transparent failover that can happen on the logical layer as well.
So your application layer has dual configuration.
Yes, yes, yeah. And if we look in, let's find it. Yeah, it's fine. Okay, thank you. So last one, let's look at, let's go back to exit presentation mode and basically look at how my application services layer is configured. Yeah, source, main, resources. So I have a configuration for connecting as a client to cluster A configuration of connecting to cluster B. I'm joining those two configuration. I'm putting cluster A as XML first and cluster B second. The other thing I'm doing is I'm creating a reconnect strategy here. So basically what I'm saying is you have 10 seconds to reconnect to the cluster. If you don't, go to the backup. Okay? So retry whatever the backup algorithm is for 10 seconds. If you don't, then go to the backup. So I'm going to do a kill on cluster A, and we should see what we're looking for is consistency, right? So the number of transactions we're tracking in that front end, we want to make sure is consistently climbing. And so that means the transaction producer and the clients that's pulling into the web layer is all failing over. So basically what he's going to do is just take a list of the PIDs of the members and do a kill -9 on them. Yeah. Let's see what happens. See, the back off period starts here. So this is the transaction simulator. This is our web, and you can see, yeah, I just connected to cluster B after 10 seconds. You see my RESTful layer here is connected to cluster B. So I'm actually listening to this activity. I have something called that lifecycle listener, and it's telling me, hey, you just changed clusters here. And then that starts going. So here's my so I have a listener that's listening to the changes the transactions are doing. So that is re-registered on the new cluster, and automatically what we're looking for is our front end looking as sharp as before without any flat lines. So it keeps going. So we didn't, you should see like a pause for that 10 seconds, but it will still go on. There's no discrepancy in the number of transactions in both cluster, right? So one is not higher than the other, so there's no change in the dip. There's no dip in the, since I was writing to A would be the most recent number, but in 10 seconds I was able to recover and there was no change in that number. Now, is that good enough for a credit debit type of transaction in multiple data centers? No, probably not. The bank is not going to go for that. But for most use cases, this type of resiliency is what they really want to see, and it's more than what they currently have, and it's also the ability to take advantage of modern cloud container-based environments like Kubernetes and Docker. Dynamically giving your services. Now it says, well, now, okay, what if the cluster A comes back? How do I get it back, right? So I can bring back cluster A and then kill cluster B, and it should come back. So the reverse also is possible. So let's try. I keep doing this. real quick as fast as we can. So one thing about the replication that's asynchronous, it's a delta, right? So all the transactions that are happening now are new changes that's in the queue to be sent back to the other side. But what about the data that wasn't touched, right? And that's where you do, like, when you recover that cluster, you do a full sync, and then you can kill the other guy. So we have an API that allows you to do a full sync. What am I? So I want to sync from B to A. So the A's back up. I can check. So one of the other things people don't check, and especially in Kubernetes, is we have health APIs on the REST level. They can see the health of your clusters. So if I go back here, I can see both A and B is up. Okay. I can see also that I have the two clients. My microservices, my web end is connected to that guy. So now I think I'm safe enough to do the sync. So I initiate the sync. Again, your best friend is metrics. You can go view the data and storage maps.
What happens if cluster B dies before you sync to A?
Yeah, hopefully I have a persistence layer, whether it's a system of record or Hazelcast can do it on a file basis per node. Yeah, excellent. So, yeah, good questions. Yeah. So now I've done that, and now I can go ahead and do a stop on cluster B, and everything should fail back to cluster A again, and we'll see that in our clients, transaction client. Yes, yeah. Losing nodes. Back off now. 9, 10. It's not moving. There we go. And now he's doing transactions again. And the same thing should have happened on our microservice layer. We're now back connected to A. And hopefully we haven't lost any data through all that chaos that just occurred. And we're still moving. So resiliency. Any questions? I'm Joe at Hazelcast. If you guys have any questions, Hazelcast is Spring Boot friendly. There's a Spring Boot Hazelcast. You can Spring Boot Hazelcast automatically by including that into your applications. Whether it's you're using Micronaut or you're using Spring Boot, it both works. And you can Spring Boot as a client, where Hazelcast is a server process or service running somewhere else, and your application is a client retrieving and putting data into it. Or you can actually have the members run Spring Boot as a member. So each of your microservice instances will be a member with a distributed data set across them. Okay? Thank you.